Hello students, so this particular question was asked from electrical machine section in your gate 24 EE. Okay, in this question they are asking that a 3-phase 50 Hz 6-pole induction motor runs at 960 rpm. Okay, the stator copper loss, core loss and the rotational loss of the motor can be neglected. The percentage efficiency of the motor. So very simple question it is. Okay, it is asked from the induction motor and they have given that frequency is 50 Hz, number of poles are 6 and the motor runs at 960 rpm. So they have given the rotor speed and the synchronous speed you can find it from 120 f by p. So 120 into 50 by 6 it will be 1000 rpm, right? So you can find out the slip. Slip is equal to ns minus nr by ns. So 1000 minus 960 is 40 divided by 1000. So that you are getting it as 0.04, right? Now they are asking you the percentage efficiency. You know that the percentage efficiency of the induction motor is given as the ratio of output power by input power. Now if you remember the power flow diagram, okay, from the power flow diagram, this output power can be equal to this rotational power or mechanically developed power, because you can see that the rotational loss has been neglected. Okay, and this input power can be written as the air gap power. Yes or no? Because when the rotational losses are neglected, okay, rotational losses are neglected, then Pm is equal to P naught, and when stator losses are neglected, because stator copper loss, core loss both are neglected, then Pi, that is input power, is equal to air gap power. Okay, so Pm by Pg can be written as, I know that the relationship between Pm and Pg is, it is equal to Pg into 1 minus S. So the percentage efficiency you will be getting it as 1 minus S into 100%. Okay, this was just the efficiency. Percentage, if you're writing, you have to multiply it with 100. So 1 minus 0.04 into 100%, that will come as 96%. So option C is the correct answer. The percentage efficiency of the motor is 96%. Okay, end of the question. Hello students. So this particular question was asked from the electrical machine part in GATE 2024 EE. Okay, here they've asked a question from the transformer polarity. In this question, they are asking that which one of the following options represent the possible voltage polarities in a single phase two-winding transformer. Here Vp is the applied primary voltage, Ep is the induced primary voltage, Vs is the open circuit secondary voltage, and Es is the induced secondary voltage. Now if you see here in the diagram, okay, this Ep is given here. Wherever dots are given, that is considered to be positive. Okay, so if I am assuming positive here, okay, then I have to assume positive here. Okay, but here you can see that it is not matching. Okay, because by dot convention method, dots should be placed on both sides at same polarity. That means if that is positive, it will be positive, and if you have placed one dot as negative, it will be negative at both the sides. Okay, here in all the option, if you check, okay, here I am getting plus Vp, okay, and this is minus Ep. That indicates that Vp and Ep are opposite in phase, and that we already know from the phasor diagram of transformer, that the applied primary voltage and the induced primary voltage are opposite in phase. So this one is correct, but here if you see, okay, so this is plus, this is minus, and this is plus, this is minus. Okay, so here if you see, the ES and VS are opposite in phase, so that is not correct. Okay, because the secondary side induced voltage and the secondary side output voltage are in phase, right? But in option D, if you check, then you can see that VP and EP, because dots are placed here, so plus minus, and here you are getting plus minus, so VP and EP are opposite in phase, so that is correct. That is correct. And here if you see, this is plus minus, okay, and this is minus plus. So option C, because here if you see here in the option D, this ES and VS are opposite in phase. If you see the dot polarity, because wherever dots will be placed, I'll place it plus positive sign, so plus minus, and this is minus plus, so these are in opposite phase, so it will not be taken. So option C, if you see option C, I can see here that positive is placed here, negative is here, and this one is also positive negative, which means that VS and ES are in same phase. So that is also correct. So from the dot convention, I am getting option C. Okay, because here you see this is plus, this is minus, and this is plus, this is minus. So in option C, I am getting the VP and EP opposite in phase. So that is correct from the phasor diagram, and ES and VS are same in phase. So that is correct. So option C is the correct answer for this question. In none of the option you are getting these two fundamentals which are present in the phasor diagram of a transformer. Okay, end of the question. Hello students. So this particular question was asked from the electrical machine part, okay, in GATE 2024 EE. So this question has been asked from synchronous generator. So here they are asking that a three-phase 11 kilovolt 10 MVA synchronous generator is connected to an inductive load of power factor root 3 by 2 via a lossless line with per phase inductive reactance of 5 ohm. Okay, the per phase synchronous reactance of the generator is 30 ohm with a negligible armature resistance. So armature resistance is negligible. Okay, the line is having an inductive reactance of 5 ohm, and the per phase synchronous reactance of generator is 30 ohm. If the generator is producing the rated current at the rated voltage, then the power factor at the terminals of the generator. Okay, at the terminals of the generator they are asking, which means if I just draw the diagram, the equivalent circuit diagram of generator, synchronous generator. So here I am having my synchronous reactance. I am just drawing for synchronous generator. Okay, this is my synchronous reactance, and armature resistance is neglected, so I will not consider it. And this is my terminal voltage or the load voltage. Here I'll connect the load. Okay, now here I know that it is given as E angle plus delta because it is a generator. Okay, otherwise if it is a motor, I'll denote it as E angle minus delta. Okay, and these are the terminals of the generator. Okay, terminals of generator, and this is given as Xs is equal to 30 ohm. Okay, and this is my load, and at the load side I'm getting a terminal voltage of how much? 11 kilovolt and 10 MVA. So here I am having 11 kilovolt. Okay, so now I am given the rating of the generator, and this is VT angle 0. The terminal voltage is VT. Okay, so the ratings of generator they have given as 11 kilovolt, ratings of synchronous generator 11 kilovolt comma 10 MVA. Okay, so I know that the rated voltage in three phase is given as root 3 V rated into I rated, root 3 into VL into IL. That is how you give the rating of the three phase generator. Okay, so in here this is 10 to the power 10 into 10 to the power 6 is equal to root 3. V rated is 11 into 10 to the power 3, because this is nothing but line voltage. Okay, root 3 VL IL. Okay, this is nothing but root 3 VL IL. So I rated, I can get it from here. So I rated will be equal to 10 into 10 to the power 6 by root 3 into 11 into 10 to the power 3. If you solve this, you'll get it 524.86 ampere. Okay, now I know the phase voltage can be written as line voltage upon root 3. Line voltage is 11 into 10 to the power 3 divided by root 3. So that I'll get it as just 11,000. I'll write 11,000 by root 3. Okay, angle 0. So the terminal voltage, the phase voltage, I have to denote it here. So angle 0. 11,000 by root 3, angle 0. Now I can apply the EMF equation. Okay, so in the EMF equation, I get it as V phase, that is the terminal voltage, is equal to under root of VL cos 30 plus IA into RA. IA into RA is 0 because the armature resistance they have neglected, plus VL sin 30 plus, this is square, and plus IA into XS. XS is given, that is why I have taken it, and V phase is 11,000 by root 3. Okay, so if I square it, here the square will, under root part will go. So VL is, you have to find it. Okay, and this particular part is cos 30 is root 3 by 2. So I can write root 3 by 2 is root 3 square is 3 and 2 square is 4. 3 by 4 VL square plus, and this is A plus B whole square. So I can write it as VL sin 30 is 1 by 2. So VL by 2 whole square is VL square by 4. Then IA into XS. IA into XS, if you do, IA is known to you, I rated you have already got. Okay, so 524 into 86 into this XS, that is 5. If you do it, you and then square it, you'll get it as 6886950.5. Okay, then a square plus b square plus 2ab. So 2a is VL. Okay, sin 30, that is half. So 2a into b. B is IA axis. IA into XS is, so this and this will get cancelled. IA axis is 2624.3. Okay, so from here, if you solve this, you'll get VL equal to 4618.12 volt. Okay, then I can find tan of psi. is equal to VL sin 30 plus IA excess divided by VL cos 30. That is how you get the value of psi. So from here, I'll get it as, if I solve this, 1.2335. Okay, and from here I can get the value of psi. Psi will be equal to 50.968, and I know that for this generator, if you remember the phasor diagram, this psi was equal to delta plus phi. Okay, but delta is the internal load angle. Okay, and phi was the power factor angle. So power factor is already given to you and psi is known to you. So you can get the value of delta from here. Delta will come out to be 20.968 degree, because already they have given you the inductive load of power factor root 3 by 2. Okay, so this part already they have given. Cos phi is equal to root 3 by 2. That means phi will be equal to 30 degree. Okay, from here I got, so 50.968 minus 30 will be your delta. Delta is 20.968 degree. Okay, but they are asking you the power factor of the load, power factor of the at the terminal of the generator. So at the terminal of the generator, power factor at terminals of generator, the power factor would be cos of delta. So cos of 20.968, and that will come out to be 0.629, and that is lag, and I can approximate it to 0.63 lag. So this is the power factor that I am getting, 0.63 lagging. Okay, so option A is the correct answer. End of the question. Hello students. So this particular question was asked in your electrical machines, okay, in GATE 2024 EE part. In this question, they are asking that a three-phase star-connected slip ring induction motor has the following parameter referred to the stator. They have provided you with the stator resistance, stator reactance, the rotor reactance referred to the stator, and the rotor resistance referred to the stator. Okay, this is what dash means. XR dash means it is the rotor reactance referred to the stator, and this is the rotor resistance referred to the stator. The per phase stator to rotor effective turns ratio is 3 by 1. Okay, so what is given is RS equal to 3 ohm, XS equal to 2 ohm, XR dash equal to 2 ohm, RR dash equal to 2.5 ohm, and they've given the turn ratio of per phase stator to rotor. Okay, the turn ratio will always be in per phase. Okay, whenever you are dealing with three phase system. So the per phase stator to rotor effective turn ratio is 3 by 1. Now the rotor winding is also star connected. Okay, the magnetizing reactance and the core loss are neglected. Now to have the maximum torque at the starting, the value of extra resistance in ohm referred to the rotor side to be connected in series with each phase of the rotor winding is. So what they are telling is, for maximum torque, during the start, I know that the slip for maximum torque will be equal to 1. Right? So I know the slip formula whenever you are given with the rotor resistance and the stator resistance and reactances. So here the stator resistance is not neglected and the stator reactance is also not neglected. So I'll provide the total equivalent formula will be RS square plus XS plus XR dash whole square. Okay, when RS and XS are neglected, in that case SMT is RR dash by XR dash. Okay, or RR by XR. Okay, when these two are neglected. So when these two are neglected, I'll just write RR by XR or R2 by X2. Okay, but here they are not neglected, they are considered. So that is why I have written the total formula. Okay, this was the approximated formula by neglecting stator resistance and stator reactance. Okay, so I know that this is one, and they are telling that here with each winding of the rotor you have to add some resistance. Okay, so what is the value of extra resistance? The extra resistance you have to connect in series with the each phase. So this is for each phase only we are writing. Okay, for each phase. So this will become RR dash plus R external. Okay, RR dash plus R external, because the rotor resistance is not only RR dash. Here you have connected it with the external resistance with each phase. Okay, in series. Okay, in the rotor side. So RR dash is 2.5. R external you have to calculate. But here R external is referred to the stator. R external referred to stator, because it is here the rotor resistance is referred to the stator. So R external, when you are adding it with this, so this total resistance are referred to the stator only. Okay, but they have asked it referred to the rotor side. So first I'll calculate R external referred to the stator. Okay, this will be RS square is 3 square plus XS plus XR will be 4 square, 2 plus 2. So this will become under root 3 square plus 4 square is 5, and this is 2.5 plus R external. So this is R external referred, or I can directly write it as R external dash. Okay, R external referred to the stator. So R external dash, I'll get it as 5 minus 2.5, that is 2.5 ohm. Okay, but this is not the correct answer, because in the question they have asked the R external in the rotor side. So now I have to divide with the turns ratio, and the turns ratio was 3. So 2.5 by A square. So 2.5 by 3 square. So 2.5 by 9, and that will be coming as 0.227 ohm, or I can write it as 0.28 ohm. This is 0.277. So it will come out to be 0.28 ohm. So I have rounded it to 2 decimal. So the value is 0.28, and they've asked in ohms only. Okay. So this was the correct explanation of this question. Okay. End of the question. Hello students. So this particular question was asked from the electrical machine section in your GATE 2024 EE. In this question, they are asking that a 5 kilowatt 220 volt DC shunt generator has 0.5 ohm armature resistance, including the brushes. Okay, including brushes. The motor draws a no load current of 3 ampere. Okay, so here what they have given is, first of all, let me draw the shunt excited DC machine. So shunt excited DC machine would be looking like this. This is my shunt field winding having shunt field resistance, and this is RA, armature resistance. This is a shunt motor, so current will go into it. So this is my IA, this will be my IF, and the line will be providing the current IL, and this is 5 kilowatt, the terminal output they have given, and 220 volt. Okay, so this is the diagram for shunt excited DC machine, right? Now what they are asking is, here the motor draws a no load current, means IL, okay, no load, IA, no load, the motor draws a no load current, so it draws, that means it is a line current. So IL at no load, it is given as 3 ampere. Okay, the field current is given as 1 ampere, so this is 1 ampere. Okay, and this at no load, it is 3 ampere. Okay, and this can change when you apply the load over here. Okay, here only you apply the load. So here you can see that if I try to find IANL, that will be IL is equal to IA plus IF. You know that IL is equal to IA plus IF. IF is given, and that is independent of the load current. Okay, IF is independent of the load, but IL is dependent, and here the no load current is 3 ampere. So IA at no load will be 1 ampere. Remember that whenever you apply load and change your load, this IL and IA will change. Line current and the armature current changes. Okay, so INL is coming as 2 ampere, because this was 1 ampere, this was 3 ampere. So IA no load is coming as 2 ampere. So no load induced EMF will be, core and rotational losses are constant and independent of the load. Yes, we know that. The current drawn by the motor while delivering the rated load. Okay, for the best possible efficiency. Okay, so no load EMF is, no load EMF will be terminal voltage minus IA no load into RA. RA is given to you as 0.5 here. VT is 220 volt minus IA no load is 2 ampere and RA is 0.5. So you are getting it as 219 volt, 219 volt. So you can calculate the developed power at the output, the developed power at no load. Okay, so developed power will be equal to no load EMF by no load current. Okay, no load armature current. So the back EMF here is coming as 219 volt, and no load current, no load armature current is 2. So 2 9 18, 2 3, 2 to the 4, 438 watt. Okay, and this developed power is equal to the rotational loss plus core loss. This is your developed power, and developed power at no load is equal to the rotational loss plus core loss. Okay, now they are asking that for the best possible efficiency. Okay, for the best possible efficiency, what is the current drawn by the motor? That is IL at the rated load they are asking. They are asking IL, find IL at rated load. I know that IF will remain constant. The shunt field current will remain 1 ampere. If I am able to find IA at rated load, then I'll be able to find this particular part. So I know that for maximum efficiency or best possible efficiency, the constant loss is equal to the variable loss, right? Constant loss will be your field copper loss, shunt field copper loss, plus rotational loss plus core loss, and the variable loss will be your copper loss. So shunt field loss will be VT into IF. Rotational loss and core loss already we have found from the developed power, no load developed power, that is equal to 438 watt. 438, and copper loss will be IA rated, because here IA full load you will take. Okay, rated load or full load, IA square into RA, and RA is nothing but 0.5. Okay, so VT is 220, IF is 1 plus 438, it equal to IA FL square into RA is 0.5. From here you will get the value of IA rated, okay, at rated load, and that will come out to be 36.276 ampere. Now, since this part you have calculated, so this part is coming as, this particular part IA rated load is coming as 36.276. Now you know that IL would be equal to, this IL would be equal to IA plus IF. This would be constant, but this will be changing with the load, this will be changing with the load. So IL at rated load will be IA at rated load plus IF. So 1 plus 36.276 will give you 37.276 ampere. So the answer for this question is 37.28. 276 was there, na? 276. Yes, 276. So 28 I have written. So this is the current which is drawn by the motor at the rated load. Okay. So this was all about electrical machine. Okay. End of the session.